of these basis functions models. We've been looking at these linear models which create nonlinear functions. So what we'll start by doing is just having a look at what we've been doing before, which is a reminder from I think week 4 or 5. So this Bayesian approach on the Olympics data with polynomials. So the idea in that case is we had a sort of basis function expansion, and then we were choosing a prior on the weights of those polynomials. So in this case, I've said, okay, prior with alpha is equal to 1 and a noise variance of 0.01. So just to show you what those fits look like, these are actually slightly different from the ones we did because they're ones I did like a couple of years ago, but it's the same idea. What we were able to get is this posterior distribution over the polynomial fits. And what I'm showing here is, I think, 2 standard deviations of error around that posterior mean. So you're seeing the posterior mean, which is something we computed in class, and standard deviations of error either side. And what was nice was that we were able to sort of show that even for sort of quite, I think we went in the lectures, we went up to like a 20th order polynomial or something. And when we were looking at cross-validation errors, for some reason isn't appearing here, we were finding that we were still with very high order polynomials, we were able to do something. So we were getting around overfitting by integrating over these W parameters. And that's the Bayesian approach. This approach I'm very keen on. Okay. So, okay. This was the same thing, but this is the sort of extrapolation. So the Bayesian solution was something of this form, where we were getting a mean, a posterior mean for W, which, if you compared to the maximum likelihood solution, which was a point solution, there's this sort of relationship between them. We're gaining this sort of alpha. If you take the alpha out, then the sigma squareds cancel, and you get the same solution. So if alpha, in this case, goes to infinity, so a variance of infinity in the prior, you find the posterior mean in that limit would tend towards the maximum likelihood solution. Now, in the case that alpha isn't infinity, then what actually happens is that this posterior mean is pulled closer towards 0. And so alpha I is, or alpha is sort of regularizing the solution, keeping it closer towards 0. Let's see. So what I'm going to talk about today is Gaussian processes. And Gaussian processes, I'm going to start by introducing it in a different way to what I've just described, but I'll try and give you a quick overview of how it actually relates to these polynomial models. Now, I've got a lot of lectures online where I go through an introduction to Gaussian processes in probably about 2 hours. And I still don't cover everything there. So in an hour lecture, I'm not going to be able to cover everything. But I just want to give you a sort of idea of what's going on, and then you'll have the lab class to sort of play with them. Because they're really powerful models, and they generalize a very large cross-section of models. So the way I'm going to, or the way what I've just said so far is, okay, they're related to basis function models, but they turn out to also be related to models in signal processing, so-called autoregressive models, or ARMA models, autoregressive moving average. They turn out to be related to signal processing models in the spectral, in the sort of Fourier spectrum of how data's. They was at this NIPS conference last week, which is the big conference in machine learning, and I thought it did occur to me that it's kind of really shocking how little people know about Gaussian processes and how dismissive of them they are, when very often they are using a model that is a special case of Gaussian processes. And I was trying to think about why this is, and I think it's maybe because the name Gaussian is quite off-putting. I think whenever you say it, you say Gaussian process, and it's like, I was thinking a lot about these last few weeks about implicit bias. So implicit bias is like where you make judgments about people without even being conscious of what you're doing. And it leads to like sexism and racism and all sorts of things. And I was wondering if there's something like implicit bias going on against Gaussian processes. Perhaps less worrying than sexism, racism, modelism. People somehow, I think when they see the Gaussian word, they think, oh, it's not interesting because it's Gaussian. And then they freely go away and use a model that is a special case that they didn't realize of a Gaussian process. There are reasons that not to use Gaussian processes in their most general form, because computationally, they're quite heavy computationally. They're n cubed, where n is your data, in the worst case. But that's an algorithmic reason. And one of the things I've always tried to emphasize in this course is the separation between model and algorithm. So even if you don't use them in an algorithmic reason, you should be aware of their utility as a model, as a modeling framework. You have to know why you're not using them. So often people will say, I'm not going to use a Gaussian process, I'm using a Kalman filter. Well, a Kalman filter is a Gaussian process, right? It's just a particular implementation. Or a basis function model, a standard one, is a type of Gaussian process. It's just a particular implementation. So what we're going to do is we're going to look, to give you the idea of a Gaussian process, we're going to look at a sort of single sample from a Gaussian distribution. So the Gaussian distribution is going to have a particular structure, and it's a 25-dimensional Gaussian, so it's a multivariate Gaussian. And then we're going to take one sample. So the one sample, because it's a 25-dimensional Gaussian, has 25 values. We're going to plot these values against their index. So this is doing that. Now, what we have on the left is the samples from 1, 2, 3, 4 up to 25. Right? What we have on the right is the covariance of the Gaussian that I sampled them from. So what you should be seeing here is that covariance has a particular structure. So we could order these in any way, right? The Gaussian doesn't tell you how to order its samples. But I've chosen to order them in such a way that the covariance matrix looks like this, such that neighboring points are highly correlated with each other. And as you go away from the neighbors, the correlation drops. This is a covariance matrix, but it's also a correlation because it's normalized. It's got ones down the diagonal. So a correlation matrix is like a normalized covariance matrix. So this is the correlation matrix. And this is the degradation of the correlation as you move away from the point. So the interesting thing about the sample is it looks a bit like a function, doesn't it? I mean, you could hallucinate very easily a function. It's not a function because it's a set of discrete points, whereas a function would be, a real function would be a sort of right across the real line. But it looks like it's a function. And I think that this is an amazing thing to do. We've sort of hinted at doing it in the basis function stuff, and you'll see sort of why it happens. But most people, if you're used to Gaussians, should be surprised to see such a smooth thing coming out. Most people will be surprised to see such a smooth thing coming out. And it's a nice exercise to do. I mean, I think it's the first time you do it. It's kind of like, wow, you can represent that sort of shape with a covariant structure. I think people are generally surprised at that. So let's explore a little bit why that is. So I'm going to look at these 2 points here, F1 and F2. And what we're going to do is we're going to look at their covariance. So what's the covariance of F1 and F2? Anyone tell me? Property, it's a special property of the Gaussian. To get the covariance of F1 and F2, this is representing, the mean is 0 in this case. I'm not sure if I've emphasized that. So this is all you need to know about the probability distribution because it's mean 0. So the covariance of 2 points F1 and F2, if the mean 0 of all 25, what will be the mean of those two? 0, yeah. So the mean of F1 and F2 will be also 0. How do we find the covariance? So this is the covariance of everything. How do we get the covariance for those 2 points? Very simple. So what would think of it this way. We use correlation all the time. What would the correlation be between F1 and F2? These are the correlations between every point. Yeah? So what's the correlation between F1 and F2? Does the correlation change if we integrate out the other variables? No. Whatever that distribution is, it has to have the same correlation. In fact, correlation is really fundamental. That's why people quote it all the time, because it doesn't change, like, depend on other variables. So the correlation is actually just these elements here. The covariance of those two, that's a really important property of the multivariate Gaussian. That's why we use it all the time, because it's trivial to integrate over. So integrating over F3 to F25, we get a new covariance, which is just those 2 points there. Okay, so if we're looking at the joint distribution between F1 and F2, this is the joint distribution. And then just to give you an idea of the numbers here, you can see that the correlation's high. The covariance is 11.96587, so about 0.97. So there's a very high correlation between F1 and F2 in this model. Now that's a two-dimensional Gaussian. So to give you an idea of what's going on between F1 and F2, I want to show you this contour, right? So this Gaussian here is now being represented. This says F1, it's off the page. This says F2. So this Gaussian here is represented by this covariance matrix, which is also a correlation because we've set the unit to be 1, right? So at this corners here, it's 1 and 1. So if we were to look down on from F2, we would see a Gaussian distribution with a standard deviation of 1. And if we were to look down from F1, we'd see a Gaussian distribution with standard deviation of 1. But because of this strong, so that's the marginal variance, yeah? If we were to look at just look at one variable, that would involve removing a row and a column. And then you just see that you've got a variance 1. That's the marginal variance. But you've got this strong correlation. So I often think of these shapes as like this hill, whose name I often don't get wrong. But let me try getting it. Uhuluru. Oh yeah, I forgot it. There we go. So this is how I think of what you're looking at. Okay, I know it's not very Gaussian in shape. But so it's not that Gaussian really, is it? But I like the fact that it comes out of the ground. It's in Australia, right? In Britain we normally have a member of the royal family standing in front of it when you see a picture of it. Look, there's lots of those. William Uluru. Oh, images. There you go. Charles and Diana, Uluru. Yeah, you see everyone standing in front of the rock. Anyway, so don't think about royals in front of it though, because the rock itself is far more beautiful than any royal could ever be. It isn't actually, it's not very Gaussian. It would come down like that if it were Gaussian, wouldn't it? But it's more like a Gaussian with a couple of sigmoids. It'd be more like actually what you would get as a posterior for logistic regression, actually, ignoring these bumps. But what I like about it is when you're looking at it like that, you always see it from this point of view, which there must be the tourist center right beside it or something, because you keep seeing it from this point of view. But you can't really tell the shape of it, can you? You can't really tell whether it's twisted towards you, whether it's round, or whatever else. And that's the sort of picture you're getting when you look at the marginal Gaussian distribution. If you were to look from maybe this side, maybe it'd be really narrow, yeah? We can't tell. So that's what happens when you're thinking about like the marginal distribution in this case. That's what's going on for you. You're sort of seeing... sorry. You're seeing... So I'm showing you the contours, but what I want you to think about is that it looks like Uluru. But as you went around, you can't tell whether it's circular or not from that side. So now we're seeing it from the top, and we're seeing in this case it's actually not, that there's this strong correlation between the two. Now machine learning I've talked about before is really from a probabilistic perspective. If we take the probabilistic perspective on machine learning, then all we think about is that machine learning is simply trying to model the joint distribution between variables we're interested in. So I'm just looking for the pens. So a joint distribution typically that we'd be interested in would be P of y1, y2. Where these are two variables, and the training testing could be that we want to predict P of y2 given y1. Now here I've written f because we're not putting noise in. This is a model over functions. Y we normally say is our noise corrupted. So let's just look at f2 given F1. So what we've got drawn on the board is the joint distribution between F1 and F2. But what I think we should be looking at is the prediction of a test data point F2 given something someone's told us. So you tell me the function is at that point F1 3.4, or as it's going to be minus 0.3 or something, and I now need to predict for the test. So that's actually writing the conditional distribution down. So we observe that F1 is minus 0.313, so I've drawn that as a line on the F1 axis. Now what F2 is, you can think of as because apparently it's a sacred rock, and you shouldn't do this anyway, even if it weren't sacred, someone sliced through the rock, right? So the conditional distribution is like a slice through Uluru, and then you've got the conditional distribution of what F2 is given F1 and that slice. Does that make sense? So pictorially. So if it were really a round rock, then when you would slice through, you would still be at 0, 1. So if it was an independent Gaussian, it would be a big circle here. And when you slice through, your mean would still be 0. Now what happens is you renormalize that slice as well. It's not just a slice. You need to renormalize it to make it a proper probability. And so that 0 thing would just become a Gaussian, which was the same as the marginal. Now because of this sort of relationship, this correlation between them, you get a conditional distribution for F2 that says, actually now I believe F2 is slightly negative. So that's where F2 was actually in that plot, coincidentally. So this is this conditioning formula, and this is the sort of formula used for Gaussian process prediction very commonly, done in one dimension, right? Where it says that the probability distribution for F2 given F1 is Gaussian over F2, where the mean, let's just look at the mean first of all, is K12, that's the correlation between these two variables, over K11, that's the marginal for the training variable, times F1. Now in this case, K12 was like 0.97, and K11 was 1, so it's saying the mean is 0.97 times 1, times minus 0.313. So a negative mean, close to the original one. Of course, if the correlation was 100%, so if the correlation was 100%, then this would be a degenerate Gaussian. It would actually be a straight line. If you drive the correlation to 100%, then this contour would just get narrower and narrower and narrower. And actually you would lose all probability mass off the diagonal. It would be like a straight line. And that comes if you set these two values to 1. So if you set those two values to 1, then you would see that this Gaussian distribution becomes 1 over 1 times F1. If the correlation is 100%, it would say the mean is equal to the observed value. But if the correlation is anything less, then you get this sort of regression away from the observed value back towards the prior mean. It pulls it down a bit, 0.97 over 1 times F1. Now, that's the first term. This second term there, K22 is 1. So if K12 is 0, if there's no correlation, then this term is 0. You just get the prior variance. So if K12 is 0, you get 0 over 1 times F1, which is 0, and then you get K22, the prior variance. But here it's 0.97, so like 0.93 or something, I don't know, when you square it, over 1. So you're losing a load of posterior mass, right? So this is like 1 minus 0.93. So the variance of the result is 0.07. It's a small variance because of high correlation between the two. If the correlation between the two was 1, this would be 1 minus 1 over 1. So basically, if the correlation between the two was 1, it would be the prediction for F2 is exactly the same as F1, as the correlation's dropping away. And these are actually, sorry, these are strictly speaking covariances, but because they're being normalized a little bit here, they're correlations. So that's where the covariance of the density between the two is given by this. So this is the 0.97, this is the 1. Is that sort of clear? So embedded in that covariance matrix is the relationship between, everything is zero mean. You can do this with Gaussian means as well. It just gives you a load of, so instead of F1, you get the mean of F1 appearing here, and you get the mean of of the prior mean appearing here as well. But it's simpler without the means, right? So the correlation structure is giving us this relationship. Now, this is the way, this is sort of inference in Gaussian processes. If we sort of look at a point that's further away, so the correlation is lower, so this is This is considered a reasonable correlation. This is something that that an experimenter might be excited about. You know, we find that the correlation between, I don't know, what do people look at for correlations? Pollution and lung-related deaths. If there's a correlation between those two of 0.57 or something, we'd probably be like, oh, okay, great. You know, so pollution is related, perhaps related. You don't know it's causal, but you might say that there's a significant result in terms of correlation. But it's actually a much weaker distribution. Look at that. So basically now if we know something about F1, this is the same thing about F1, what we know about F5 is much more diffuse. Because bear in mind that variance before, the variance of this posterior is going to be 1 minus 0.57 squared over 1. So because of that squaring, something, this is going to be like 0.75 is the variance here. Whereas before it was like 0.07 for that very high correlation. And indeed, when we look at the value of the function from that original plot, let's just go back to the original plot. Look, the value of the function at F5 is not even in the same half space, i.e. it's positive, whereas our original value was negative. Right? So this is still strongly correlated, but not really strongly correlated. It's only when you get very, very high correlations that you get points very close. So by the time you get down to sort of F, let's say F8 or 9 or something, the correlation is actually not 0. There's a very small number in here, but it's almost 0. So what's that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. About 11 points away. So by here, there's sort of no correlation between the two. They're pretty much statistically independent. But even before then, they're sort of looking only loosely related to those first points. So that's how the Gaussian process is specifying its function. It's talking about the correlation between different points. And in general, you get formulae like this. So they look ugly because they're all K's. But they're not super complex. And I'm not asking you really to remember these for this course. But this is the prime set of linear algebraic operations to do this in the multivariate case. So what I just sort of went through was if I give you F1, you have to predict F2. If I give you a vector of f's for this function, I haven't said why it's a function or how it's a function yet, then, and you want to predict over a vector of f stars, this is the general formula. It's like the previous one, but the previous one there was a scalar here because there was just one observation. And in the matrix case, in the vector case, there's a matrix inverse. So it's k star f k f f inverse. So if you were trying to predict over f, for example, you can see immediately this would be kff times kff inverse, which would just give you I times f. And then on this side, you would get kff times kff inverse minus times kff. So that would just be kff, and then you'd get 0. So if you were to predict where at f itself, you would find that you predict that the result is f with 0 variance. But as you shift away from that f, if you predict at other locations, then you start getting uncertainties appearing in. And this is like the, I don't know, this is like the prime inference formula for Gaussian processes. The challenge with it is that it involves this inverse of the covariance of your training data. And this is always going to be n by n. So this inverse leads to something that's n cubed in practice. And this is the headache we have with Gaussian processes. If you do them in general, you've got this n cubed inverse. If you, many practical ways of doing Gaussian processes on a large scale, like basically what people do in signal processing, or Kalman filters or whatever, turn out to be fast ways of computing matrix inverses for particular structures of KFF. But this is the most general thing. And the thing about those things is they're hidden under names like Kalman filter or whatever else. They still have Gaussian assumptions. They've still got all the same limitations. But they've got more limitations than this, actually. This is a more general formula. But it does have this cubic complexity. So here we're assuming that this is now the covariance of all our training data, the covariance between our training and our test data, and the covariance for our test data. So the question is, where does that covariance come from? Okay, let me stop there before I go into that question. So I've tried to write it in a sort of cleaner form here. What we're trying to do is predict on the test data given the training data. If we assume we're given this covariance between the two, right? So someone's told us that these are your test locations, these are your train locations. Forget the fact that it's a function. Just believe that this is something you want to predict about. You want to predict f star given f. These are the formula you use. Okay, questions there before I move on to where the covariance is coming from? Anything? It's a sort of different way of looking at it than what we've looked at before, right? But we sort of looked at it a little bit like this in naive Bayes. So in naive Bayes, we were looking at the joint distribution over y and x. And then we made factorization assumptions about how these things interrelated. Here we're not making a factorization assumption. We're just looking at f for the moment, and we're saying it's correlated. It's got zero mean, but it's correlated, and it's got a covariance of a particular form. Questions? Come on, it's a good time to ask questions. I was going too fast then. Go ahead.
Standard deviation for the Gaussian. This has some effect for the value of K11 or K22.
Yeah.
It's 111. That's because standard deviation is 1.
Yeah.
But in case of K22, it's 1.
So more in so in general we could set that to other values. It's just for this example, it's nice and easy if I keep the marginal for each thing the same. But yeah, absolutely. I've shown you a particular structure. So we've used this structure here to get this shape. If we don't use this structure, then we would have potential off-diagonal terms, all sorts, yeah, and then you have strong effects. So the effect of actually not having, so we've got a constant diagonal here. That means that we expect all these points to lie between two standard deviations in a tunnel. Actually, it turns out that we're building a stationary function here because of the way we've done it. But you're right, we could scale all those up so that they're larger. We'll show that in a bit. Or you can also imagine functions. If you do this with polynomials, you'll see that the actual standard deviations go flying out as you leave the -1, 1, -1, 1 area, yeah? Which we're not in that bit, yeah. Yeah, totally. You could have different values, but these formulae here are general. So I've gone through examples verbally with formula for those standard deviations, but these formulae here are general. They don't matter what you put in here as long as this is a valid covariance. As long as this is a valid covariance matrix, then these formula apply. Yeah? Other questions?
Is the covariance here the same as the kernel?
Yeah, that's we're going to show next. Yeah, so the covariance is going to be a kernel. So that's what we need to find out where this comes from. Because for the moment, we're just talking about two separated sets of values, f star and f, and talking about correlation between them. But that it doesn't have to be necessarily a function. That could be anything. That could be like predicting next year's course marks, given course marks this year. But I have to get a covariance, a correlation between those course marks from somewhere. And so that's what we'll look at next slide. Other questions? Yeah, so it's a great time to ask that question because the next issue is where this covariance comes from. And in a Gaussian process, so normally covariance matrices are just sort of matrices that we fit to data, we get them from data or something like that. In a Gaussian process, this covariance matrix is built using the inputs to the function, so our x's. So remember there's an f of x. So what we say is that if 2 points x and x prime are close together, so if the distance, this is the Euclidean distance between x and x prime. So on the previous case, that was simply the distance along the axis, right? But in general, this could be a distance in a high dimensional space. But think of the univariate case, if you like. The squared distance between the two is small, then I know this looks like a Gaussian form, but that's coincidence. Don't think that they're Gaussian processes because this looks like a Gaussian form. It just that this is such a cool e to the minus x squared pops up all sorts of places for mathematical reasons. But in terms of the modeling reasons, the fact that this looks like a Gaussian is nothing to do with the fact it's a Gaussian process. So sometimes it's called the Gaussian kernel, but we don't tend to call it that. We tend to call it the exponentiated quadratic kernel to make it clear that it's not why it's a Gaussian process. It's also called the RBF sometimes, or the squared exponential of the Gaussian. But it's got this form where the correlation is dropping off. It's not a Gaussian because it's not normalized, right? So if you ignore the alpha, if you set the alpha to 1, if x is equal to x prime, this is e to the minus 0, which is 1. So alpha was effectively 1 in the plots we were showing, because if it was the index. So what we were putting in that previous one is we were inserting the index into this function. So we're sort of saying the correlation between point 1 and 2 is given by 1 minus 2, which is minus 1, all squared, which is now 1, divided by whatever length scale we chose, which I don't remember. And then that gives us a way of filling in this correlation, this matrix. This function has to always produce positive definite matrices. So, because it's producing covariances, there's only one constraint on this function, and that's that it needs to make a matrix which is always positive definite regardless of the inputs. There's a whole field called kernel methods. And in that domain, they call these things Mercer kernels. So there's particular classes of functions you can use. If you read about kernel methods, you see there's a load of them. This is quite a widely used one. And then if we look at samples from it, what you can see is that so these are sort of functions generated using this covariance matrix, but they're being displayed in a special way. So this is my friend and colleague Philip Hennig came up with this idea. So his idea was, so we know we showed like a contour of the Gaussian in those 2 dimensions. What you're seeing here is like a journey along one of those contours, and you're seeing the nature of the different functions. Remember, on that contour you've got an f1 and f2. Yeah, so as you move around that contour, there's 2 f1s and f2. So if we just plotted those, you would just see f1 and f2 moving up and down as you move around that contour. Philip's idea was, okay, well, let's show that for the whole function. So that these contours also can exist in higher dimensional space, 3-dimensional. So imagine going around the world. So we leave Sheffield, the center of the world, and we head somewhere else in the world like the North Pole, and we do a big circle, a great circle, and take that journey. You're now in positions in a 3-dimensional space, right? If you up that again, do a 4-dimensional. So there's many circles you could take around the world. There's many, many ways you can go around the world, and include infinite ways you can go around the world and go through Sheffield, or anywhere else. Now, if you take that to a 4-dimensional case conceptually, then you can see you can do it with 4 points. So as you were going on the loop round Sheffield, at some point, Sheffield would be located in space, Euclidean-wise, in a sort of x, y, z location. That would be a 3-dimensional. If you do that 4-dimensional, 5-dimensional, 6-dimensional, keep showing that, then we're starting to see that you can do this in effect implicitly in infinite dimensional space, and you're seeing in the entire function. So this is the sort of weird thing about Gaussians. The reason it works is because of that marginalization trick I showed you right at the beginning. So conceptually, we were talking about those 2 points. We'd integrated our f3 to f25, and we can focus on 2 points only. That's a really bizarre property of the Gaussian process. It doesn't matter what f3 to f25 were or are, or that they exist. You still get a Gaussian distribution for f1 and f2. That means it doesn't matter about f26 up to f100, f100 up to whatever, infinity. It doesn't matter what other points there are. So the process itself, Gaussian processes are things that are defined across the entire real line, and you use this function to find the correlations between them. But you can never write down the whole process, right? It's an infinite dimensional object. It's a function. But you can always talk about the distribution of a finite number of instantiated observations from that function. And that's what we're doing here. Even though these look like curves, there's only 200 points or something to generate these. So conceptually, because of this weird thing about Gaussians, that the marginal of a Gaussian in 25 dimensions, it doesn't affect f1 and f2 to integrate out f3 to f25. That thing we showed at the beginning. They've got this weird property that you can keep doing that, and you can see the Gaussian distribution as a sort of finite, just looking at a little window of what the entire function was, of those discrete values that you observe, which is kind of cool, isn't it? So what you're doing is something that is kind of impossible and conceptually very difficult to think about. And if you start studying this properly, if you go into the maths department and talk about process theory, you'll find the maths gets really complicated. But you never need to worry about that. Because what you're actually doing is you're talking about a distribution over an infinite space. So they call them measures in maths if you're doing probability seriously. But we don't actually need to do that, because all we need to know is that we can look at a finite set of samples of observations from that function. No one's ever going to give you infinite data. Well, I mean, there's certain unusual situations where you might get infinite data, like a segment of the function for some reason, but that's unusual. In machine learning, typically you're going to get given a finite number of points that are hypothesized to be from this function and asked to make a finite number of predictions. So the fact that this is an infinite dimensional object doesn't bother you. You only need to compute the covariance. You've got a machine for computing the covariances, which is this function here, and you only need to compute the covariances for the points where you've made observations. So in the case where you've got a sort of, I'll go through this and then we'll pause again for questions. In the case where you've got a sort of a training and test set, so let's say you've got training data points at -3 and 1.2 and you want to make a prediction at 1.4, what do you do? Well, you take this function and you start building this covariance matrix. Once you've got that covariance matrix, you can feed it into the formula we saw before and start to make predictions. Yeah? So for this case, to start building the covariance, we need to take each point, x1 and x1, the -3 and -3. We put them in the formula, which in a rather involved way with many two minuses tells us that if we put them in here, we get -3 -3, which is 0. And then, of course, the answer is 1 times e to the 0, which is 1. So as we look at the matrix as we build it up, now we've got x2 is 1.2 and x1 is -3. So because in here it's 1.2 minus -3, which is 4.2. 4.2 squared divided by 2 times 4. So that's 16 divided by 8 or something. So that'd be like e to the -2. That'd be about right, e to the -2. So e, what is e? 2.7. E squared is about something around about 9. 1 over that is about 0.1. Yeah? So that's what we're getting in here. And of course it's symmetric, right? So this value is just the same. So we can go through x2, of course, is the same. This your question earlier. In this case, this covariance function we're using happens to always be the same. Why is that, actually? It's because it's a function of the squared distance. It's a function of the distance between the two. Now, any covariance function, not all covariance functions are a function of the distance between the two, but those that are a special class, stationary covariances. So this is a very popular class. If you look in a covariance function, you see it's a function of the distance between the two. You know that basically the location cannot matter. Like, we could compute, it doesn't matter what the mean of x2 is here, and x1 and x3. We could shift this whole sequence somewhere else, and you would get the same thing. That means it's a stationary function. That's the definition of a stationary function. So we could like add 7 to these values, but we'd get the same covariance matrix. And so that's why it's popping out here. But it doesn't need to be like that. There's other covariances functions which can be different. And then, okay, 1.4 and -3. Okay, so that's quite a long way away. So it's even lower than the value before. Now, these are close, 1.2 and 1.4. So this is with a length scale, which is 2. So L here is chosen to be 2. So this is 0.2 divided by, whatever that was, I said before, 8. 0.2 squared divided by 8. So it's quite a small value. So now we're getting strong correlation. This is obviously going to be 1, the last one. Okay? So if we look at the colors for that, what we see is that our test point here at x3 is strongly correlated to x2. So the observation of x1 will have an influence, it will have a weak influence, but basically x2 is going to have a much stronger influence because of its distance in the prediction, if we were to use it in those formulae from before. Yeah? Now in the lab class, you've got all these formulae set up in the, I believe, you'll be able to go through running these predictions. So here, I've added another data point, and it's the same. These first 3 are the same data points, but the additional, I've reduced the numbers of significant figures, which is why the numbers are slightly different. So this new data point is x4 is 2, and so So in fact, let's think of this, like, let's pretend this was actually our training set. So we already pre-computed this when we did the training, right? That's the training data. Someone comes along and says, please can I have a prediction at x4? I want a prediction at x4, right? So to make your prediction at x4, you need this row, which is the same as this column, of the covariance. That's k star f. This is kff in what we had before. And this is k star f, this is k star f, and this is k star star is this one down here, which will just be 1. So the process of making the prediction requires us to compute k star f, and then k star star. Now we have, so this block was kff, this is k star f, this is k star star. So the variance of the, at the new point is going to be k star star, which is 1, times k star f transpose kff inverse, so this matrix inverse, kf star. Okay, that, I mean, I'm not going to do that in my head for you. That'd be a question in the exam. It's a sort of question you had to answer in A-level, wasn't it? Invert this. I should make that question in the exam. But this isn't in the exam. Okay, don't worry. It's not a question in the exam. This is about, like, so you can see why, like, Gaussian processes, people knew them in the past, because inverting this 3 by 3 matrix, you only have to do it once for your training data. But that's a bit of a headache, right? Anyone have to do this at school? We used to have to know how to do this. It's just like to put you off linear algebra. Why would anyone have to do that in real life? It's just to make you feel linear algebra is annoying. 4 by 4 is, like, even worse. And we've got computers to do that for us, right? Like, think of poor Gauss and Laplace. When they looked at these things, they had to do it by hand. We do this via computer. So those are the sort of things you need to make the prediction. And then you also need, the final thing you need is the observations at these training data. And then you can use that to get the mean. And then you've got the mean and the posterior. Okay, so in that case, here's the pattern. So I won't go through. This one is just increasing the standard deviation by setting alpha to be 4, yeah? And then that will just increase the width of the functions. I'm not going to talk about covariance from basis functions, I think. Oh, or maybe I will a little bit. Yeah, sorry. I'll just briefly go through covariance from basis functions. The cool thing about that covariance matrix, I'm not going to worry about the maths. Remember, we've looked at this before. Well, it turns out you can get that covariance matrix by making the following decision. You can decide, well, here you've got to decide where mu is, right? How many basis functions and where they're located. So the really cool thing about Gaussian processes is you can show that that covariance function we've seen before arises from assuming that you're going to place these bases, these Gaussian type bases, exponentiated quadratic bases, all the way across the real line, and you're going to have infinite of them. So you remove the number choice, and you remove, remember we've seen in the polynomials that actually performance didn't get that much worse as we increase the number of bases, if we use the Bayesian approach. So what Gaussian processes typically we do is we say, we're going to use infinite of these things. We don't do it normally for polynomials, but we rarely use polynomials. But in the RBF case, we say, we're going to have infinite basis functions right across the real line. The only parameter we're left with is this length scale. Actually, this length scale here turns out to be not quite. It's like square root of 2 of the other length scale times the other length scale. It doesn't quite match. But if you remember when we were looking at the, the sort of basis function models in the Bayesian case, we sort of took samples, didn't we? Here's a bunch of samples here before. These samples are samples from the sort of Gaussian process associated with that model. It's just a specific type of Gaussian process, not a very interesting one, with 3 basis functions. So these processes relate to basis function models. That's appearing twice for some reason. Oh, because there's more detail here. Yeah, so let's look briefly at how, I mean, you've actually seen this in your notes already. So in our basis function models, we had this, right? We had the expectation, well, no, ignore the expectation signs. So in fact, ignore this. Let me just write it down, because I think that this is an old slide that I don't use anymore because it's not as useful. Right, let me just draw it on the board. So what we did in our basis function models is we said that f is equal to phi times w. That's what's written here. And then we say w is drawn from a Gaussian with zero mean alpha I. But that immediately implies, from our rules of the multivariate Gaussian, that f is drawn from a Gaussian. Now, do people remember the rules? So what's the mean of the Gaussian? If the mean of w is 0, what mean do we expect here? For computing the marginal likelihood, we did this in the Bayesian lecture. You're going to have to revise this. Yeah, so what's the mean here? 0, yeah, I heard. And what's the covariance? The covariance is the harder thing to remember, but what is it? Anyone remember? Alpha, not squared, but you're on the right track. Something's squared, not the alpha though. Phi, yeah. Phi transpose. Yeah? What's this saying? This saying f is drawn from a Gaussian distribution with this covariance matrix. This is the covariance function. It's a Gaussian process. So any Bayesian linear regression model is a particular type of Gaussian process. Only in this case, what we see is the elements of this. So if we look at K11, so this will make a matrix. K11 will be phi, let's get my notation right. Think about that. Phi colon comma 1 transpose phi colon comma 1, where this is the first row of phi, our basis function matrix. Yeah? Times alpha, sorry. And K1, so Kij, so it's a particular type of way of constructing a covariance matrix. In the simplest case, the linear case, then it's xi transpose xj. Yeah? Where the covariance matrix itself was xx transpose. If you sample from a Gaussian process with that covariance function, you will see a bunch of straight lines. But these are degenerate processes. So you can't write down the covariance we've written down, this exponentially quadratic form. You can't write it down as a sum. And the only interpretation turns out to be that it's not a sum, that it's an integral. Kij is equal to an integral over infinite of these functions along the real line. Well, an infinite sum of that type, so more than an integral. So it can be seen as an infinite sum. So in other words, the number of bases goes to infinity. So you can't write down a basis function matrix anymore. So think about this is an n by k, or do I call it m? I call it m, do I? I can't remember. By m by n in here to give us an n by n matrix. But the m disappears. So any of the models we looked at before in Bayesian linear regression, you've got m basis functions. But in Gaussian processes, you take m to infinity. So you can't write it down in this factorized form anymore. You can only write it down as one matrix, K. Yeah? So it's just a more general thing than what we did before. You have infinite bases. Okay. Let's just see what I had on the... I mean, there's just no way, I can tell you that... So, look, this is actually... relating to that. So yeah, this is cool, because this is the covariance function. This object here is the covariance function of phi transpose for those guys, yeah? So take a look. What happens is, as you leave the area where you've got data, these basis function matrices become 0, yeah? Where you've got basis functions. When you leave the area where you've got basis functions, the vectors become 0. So as you move out of the regime where there's basis functions, you just get zeros. So that's really dumb. It's saying your prior is 0. You don't expect to see anything. Where you've got 3 bases, you expect to see 3 bumps. But you can picture, as you get infinite of these and put them across the real line, it looks like that Gaussian process covariance we saw earlier. It's not actually easy to know that, actually, and this is a very odd special case. The reason that it goes to the Gaussian in this case, in such a clean way, that Gaussian goes to Gaussian, is because inside the maths, when you do the maths, you get these basis functions, one exponentiated quadratic times another exponentiated quadratic, gives us an exponentiated quadratic, sum over those things, which we convert into an integral, so that's an integral over an exponentiated quadratic, which gives us something that looks like an exponentiated quadratic. No other function does that. I mean, it becomes incredibly complex to do this for lots of other things. Like there's people, I mean, for many things you can't even do it analytically. So if you want to do a neural network type model, which people look at, and you try and put sigmoid functions in here, then you've got to multiply them and add ultimate sigmoid functions, and it's not analytic. You can't solve it. So people have done that, but they do it with probit functions instead of sigmoid functions. So be a bit careful. It's not the case that the covariance function looks like the basis normally as it does here. It's just that wonderful properties of these exponential quadratics that when you multiply them together, they stay in the same class. You integrate them, they stay in the same class. But that's really unusual, right? It's most other functions don't do that. That's why Gaussians, the fact that that's so unusual is why Gaussians are so fundamental. Okay, so this is the sort of, just to end on, so this is the sort of thing we can do in practice is, and this is like, so Tony O'Hagan, who used to be here in Sheffield, he's like a pioneer. He's an emeritus professor, he's in stats. Total pioneer of this area. I was talking about this in 1978. Other people talked about it before, but a real leader. Jeremy Oakley's still there, he's a prof in stats. And they did this sort of Bayesian analysis of computer code outputs with these models, so it's their Baco code. So this is like where we've got two observations and we're now predicting for a third observation. But you can predict everywhere along the real line. Because we're using F and no noise, our prediction goes right through the observation, yeah? Noise-free predictions. We can add noise trivially. We add noise just by adding a diagonal to K. I'm not going to go through that now, but I think it's in the lab. But here's a prediction here, and then this is the observation where the prediction was. So if I update the model given that observation, that's what I get. There's two more positions where the observations were there. If I update, I get that. And then there's a bunch more, and if I update, I get that. This is, now it's actually starting to look degenerate. So it's starting to look like the prediction is 100% confident. It is extremely confident. It's not degenerate in this case. We know that because of the covariance function I chose. But the effect here is very similar to, people know about Nyquist's sampling theorem. Anyone heard of that? Yeah, so Nyquist's sampling theorem says that you can recover a function to 100% if that function is band limited, if you know that there are no frequencies above a certain number. So if you sample at twice the rate of the maximum frequency present, you will always recover the function 100%. This is very, very similar. Only, I mean, it's an absurd idea. There's no, I mean, how do you know that there's no frequency above a certain number? Well, it turns out that that Nyquist thing is a Gaussian process assumption. And it's a really bad one to use in practice. So in practice, you can also create these covariance functions by thinking of filters in Fourier space. And that Nyquist band-limited assumption is a filter in Fourier space saying nothing above a certain point. The covariance function that's associated with it is a really poor one to use. You shouldn't use it. But you can use it to prove this Nyquist sampling theorem. So the whole of signal processing, all of signal reconstruction, is based on Gaussian processes with a very poor choice for covariance function, basically. It's something, the form of the covariance function is the sink, because you need to inverse Fourier transform what that filter is. There's a theorem for that. So that sort of shows you the generality. I mean, I'm not going to ask you on that on an exam, but I'm giving you an idea of, okay, basis functions go to Gaussian processes, but all band-limited signal processing, just an instantiation of a Gaussian process. And everyone, all they're focusing on is the algorithm, not the model. Okay, so I think we've got to finish there. Just to show you that the way you, to go from F to Y, you can add noise with a little Gaussian distribution here. So you say, I'm going to make an observation which has a mean of Fi and a variance of sigma squared. Saying that is equivalent to adding a covariance function of this form, right? So that is an independent diagonal covariance function. That's what noise is, right? So in these covariance functions, if you just have terms along the diagonal, for that way around, which way around, I don't know. Terms along the diagonal, yeah, like that, then that's total independence. But the beautiful, wonderful thing about Gaussian processes is if you have two functions if you believe your result is the result of two underlying functions, you just add them together. We've got to finish here. So you'll see that in the lab class. Okay? So I should probably take questions, but I've overrun a little bit and they're waiting outside.